Hi everyone, welcome back to chemistry. In this video, we're going to continue our discussion of ions. So in the last video, we left off with an example showing kind of what happens when an atom wants to lose electrons to gain its octet, right? We said atoms want to have those 8 valence electrons in their outermost shell or valence shell, and so sometimes they will lose electrons in order to do so. But sometimes they'll also gain electrons to do that, and it really just depends on what type of atom you have. So for example, here we have chlorine, and you can see on the left is a neutral chlorine atom. So looking at that on the left, we have our electron configuration for chlorine, 17 protons and 17 electrons, so no overall charge, right? And you'll notice that chlorine right now has 1, 2, 3, 4, 5, 6, 7 valence electrons, which is really close to 8, right? That octet that we want. So chlorine is so close to having that full valence shell that instead of like magnesium where it wants to lose electrons, okay, it actually really wants to gain 1 electron because it's almost there, right? It's easier for chlorine. Let's go back up to our periodic table. It's easier for chlorine, which is over here, to gain 1 electron to be like argon than to lose 7 to be like the previous noble gas neon, right? It's so close to being a noble gas, it just needs 1 electron. So what it's going to do is it's going to want to take an electron from someone else, from another atom, I should say. And when it does that, that's going to result in an overall 1 minus charge, or -1 charge. And the reason for that is, right, if we have 1 less proton than electrons, we're going to have overall, we have 1 more negative charge than positive, right? So we'll have a 1 minus overall charge. And that makes sense, right? If chlorine gained 1 electron, and electrons have a negative charge, now instead of being neutral, we're going to have an overall negative charge. And chlorine's not alone. It turns out that a lot of times elements that belong in the same group or vertical column, they're going to form ions with the same charge because they have the same number of valence electrons. So looking at that column that I've drawn an arrow to, where our chlorine is, right? Chlorine wants to gain 1 electron because it's already got 7, and it just wants to gain 1 more so it can be like those awesome noble gases. This is similar to fluorine, right? Fluorine is in the same exact boat, right? For fluorine, looking over here, if we're fluorine, it's easy for us to just gain 1 electron to be like neon, right? That's the nearest noble gas. We're so close. So we want to gain an electron if we're fluorine, right? Bromine and iodine as well. They're really close to these noble gases here, okay? So anything that's in this group 7-1A, when it forms an ion, meaning when it is not a neutral atom, the charge on that ion is going to be 1 minus, okay? Because it just wants to gain 1 electron, right? And when it does that, it'll have a 1 minus charge, okay? All right, the next column over here with oxygen, sulfur, and selenium. Atoms in that column or group, they have 6 valence electrons, right? Remember, for main group elements or tall column elements, the number of valence electrons equals the group number. So for anything in this column, we're going to have 6 valence electrons. And again, looking at our other periodic table, in fact, let me just drag this guy down here. Let me see if I can. All right, looking at this periodic table, right? Now we're looking at group 6A. So again, right, looking at oxygen, if oxygen wants a full octet and it's got 6 electrons, oxygen's going to find it much easier to gain 2 electrons to be like neon rather than lose all 6 of those electrons to be like the previous noble gas, helium. Okay? It's much easier to gain 2 than to lose 6, right? And again, right, oxygen is so close, anything in group 6A is so close to having that full octet that it's going to want to gain those 2 electrons. Okay, so anything in that group is, when it forms an ion, it's going to form a 2 minus charge. It's going to want to gain 2 electrons. Okay, same thing here in group 5A. It's easier to gain 3 electrons for a total of a 3 minus charge than it is to lose 5. As you get closer to kind of the group 4 here, thinking about our octet rule, right? We want 8 valence electrons. 4 is kind of right in the middle of 8. So it could kind of go either way. So I don't have an easy kind of trend for you there. But I do have some other trends. Remember magnesium here, right? We said was going to want to lose those 2 electrons. And when it loses 2 electrons, right, because it's easier for it to lose this and this to be like this noble gas than it is to gain this, and this, right? So when it loses 2 electrons, it's going to have that 2 plus charge. And everything in this column is going to kind of follow that trend. So they'll all form those 2 plus charges. In the 1A column, right, they're going to want to lose 1 electron. They're actually really close to being like the previous noble gas, right? So for lithium here, lithium wants to lose 1 electron to be like helium up here because it's way easier to lose 1 than to gain 7, okay? So same idea there. Anything in group 1A is going to lose 1 electron, and when it does that, it's going to have a 1 plus charge if it forms an ion. These are just some trends that we see with ions, that when these particular elements form ions, when they form some kind of charged particle, right, these are the charges that they're going to have. Okay. Oh, I missed aluminum here. Aluminum also is going to form a 3 plus charge. Some of the other ones in this category, they can do kind of like weird things with their ions, so we're not going to talk about them. For our purposes, just remember that aluminum has that 3 plus charge. All right, and then just to recap, remember I said in the last video that we have a special name for positively charged ions, and we call those cations, and a special name for negatively charged ions, which are anions. We also, specifically for negatively charged ions, we change the ending of the negatively charged ion to IDE. And then we add the ion at the end, okay? So notice for positively charged ions, we just leave it, right? Sodium ion. Instead of a sodium atom, it's now just a sodium ion, which makes sense because we now know it has a charge, and any particle with a charge to it we call an ion, right? It's no longer an atom. So sodium atom just becomes sodium ion when it has a charge. For negatively charged ions or anions, we replace the end of the element's name with IDE, and then we add ion. So instead of chlorine, right, we have chloride here. And then we just add ion to the end. Chloride ion, not chlorine ion, chloride ion. Just like, for example, something like sodium chloride. When we look at the, which is table salt, right? When we look at sodium chloride is an excellent example of an ionic compound. So what's happening, and let's zoom in a little bit here. When we make this sodium chloride compound, what's actually going on is, remember we said that anything in the first group of elements, which sodium is, when you look on the periodic table, it's in group 1A. We said anything in that group is going to want to lose 1 electron. Okay, because once it loses, it's easier to lose this 1 electron than to gain 7, right? So it's going to want to lose that electron. And when it does, it's actually going to give that electron to chlorine over here, because chlorine really wants an electron there. remember we said when chlorine forms an ion, it's going to form a 1 minus charged ion. And when sodium forms an ion, it's going to form a 1 plus. And the reason for this is because when the two bond together, sodium gives its electron to chlorine. Sodium says, hey, you know what? I just don't want this extra electron. And chlorine's like, wait, that's great because I really, really want an extra electron. And they're like, awesome, let's hang out together and then we can both be happy. And that's what happens. And then they kind of stay together because now they have this really nice difference in charge. And that difference in charge, right, pluses and minuses, they always want to hang out together, right, like a magnet. And so they're going to kind of stay together so they can both be happy. And now you'll notice, right, each of these has 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Pretty cool. Also, remember, sodium is our positively charged ion, which we call a cation. Chlorine is our... chloride is our negatively charged anion. That's why it gets the ending chloride instead of chlorine. Okay? All right, so what if we don't want to draw out that huge picture of what's going on with bonding? Well, that's when Lewis diagrams come in. It's another way that we can represent an element with its valence electrons only. Okay, so noticing, right, when we look over here at this example for sodium, when you look on the periodic table, sodium has 11 protons, right? That's its atomic number is 11, so it's got 11 protons, which means in a neutral sodium atom, sodium has 11 electrons, right? If it hasn't gained or lost any electrons, it's a neutral sodium atom, and it should have the same number of protons as electrons, same number of positives as negatives. So when we look at that sodium, while we care about the first 10 electrons, we really care a lot more about the valence electron, right? Those valence electrons, like I said, those are the ones that are participating in bonding. And we just saw that up here, right? That valence electron is the one that sodium gives to chlorine, okay? That valence electron is the one that's responsible for bonding. So that's the one that we really want to represent. So you might be looking at this and going, well, there's only one electron there, that dot, but that's because we're only showing the valence electrons with these Lewis diagrams. We're not going to draw out all of the electrons that the atom has because that would just take too long, and we don't really care about the inner electrons as much, right? So we're only going to draw the valence electrons, and for sodium, since sodium's in group 1A, it has one valence electron. And we can draw that valence electron with a little dot here. Okay, so you just kind of write the element symbol, right? And then one dot for the valence. I don't care where you draw that dot, right? You could have drawn it here or here or here. These all are saying the same thing. It's that sodium has one valence electron. Just an easier way to represent that than drawing this whole thing here. All right, let's try with a little bit of a more challenging one. So chlorine, right? Chlorine's in group 7A, right? Which means it has 7 valence electrons, okay? So if we were going to draw the Lewis dot structure or the Lewis diagram, you'll hear people say it either way. So you'll see here we've got our element symbol in the middle there for chlorine, just our capital C, a lowercase l. So chlorine, and then we're going to draw those 7 valence electrons around chlorine. Now, I'm not too particular about how you draw those electrons, right? You could have drawn it like this. You could have drawn it like this. You know, there's lots of different ways you could have drawn it. As long as you have 7 electrons around your chlorine, that's good. Also, what you do want to notice is that when we're drawing these electrons, we kind of have them in pairs or alone, okay? You're never going to want to have something like this. we find that electrons in nature, they will pair up if they have to. They'd rather be alone, right, because they both have the same charge. But if they have to pair up, they will. But they're not going to want to be that close to like two other electrons. So they're going to try to be as far apart from each other as possible. So that's why something like this would be good. But you don't want something like, you know, this. And you'll just get used to that convention as you keep kind of drawing these. All right, now pause the video and try this practice out. It says to draw the Lewis diagram or the Lewis dot structure for each of the elements in period 2 of the periodic table. All right, so for lithium, lithium has how many valence electrons? Yeah, well, lithium's in group 1A, right? So it has 1 valence electron. So we can draw it anywhere, and we'll just draw it here because that's where I'm used to drawing it. And let me zoom in a little bit here, okay? So we'll just draw it there. That's its 1 valence electron, right? What about beryllium? Yeah, beryllium has 2 valence electrons because it's in group 2A. So something like this would be good. Again, if you draw it like this, I know what you mean, but it looks a little funky. Don't pair them up unless until you have to. So they'd prefer to be alone, but they will pair up if they must. So don't draw it like that. This would be better. All right, and then boron is in group 3A, so we have 3 valence electrons. So we go 1 and 2 and 3, something like that. That looks great. Carbon, we've got 1, 2, 3, 4, right? Because we're in group 4A, so we've got 4 valence electrons. Nitrogen, we're in group 5A, so we've got 5. So we go 1, 2, 3, 4, and I'm just going to put my other one here. Notice once they start kind of having to pair up, I'll pair them up. Okay, so I did kind of 1 electron on each side of that nitrogen, and then when it was time to pair up, the electron's like, all right, fine, I'll pair up with this one. All right, oxygen is in group 6A, so it has 6 valence electrons. So let's start 1, 2, 3, 4. Now we've got 1 on each side, so let's start pairing up 5 and 6, something like that. Fluorine, we've got 1, 2, 3, 4, I don't know, 5, 6, and 7. And then neon, we've got 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8. All right, let me just actually move these up here because they look a little funky there. And I'm going to move these over a little bit. All right, that was just looking a little funky there. This too. There we go. All right, so these would be good examples of how you could draw those Lewis diagrams for each of those atoms. All right, now why did I show you all this? Well, Lewis diagrams are really helpful when we're trying to show if we're transferring or sharing electrons between atoms. So we'll talk about this in the next video because I want to pause here for a little bit, but I did want to give you just kind of a preview to let you know why we are learning about these Lewis diagrams. And they will come in handy later when we talk about ionic compounds and ionic bonding. All right, stay tuned for that, and I'll see you in the next video.